Hi, it's Jack again. We're on to Chapter 3 now. So just to remind you once more, here's where you can download the free copy of the second edition of Introduction to Theoretical Chemistry. So in Chapter 3, I talk about the shapes of potential energy surfaces. And, I think most chemists are used to these things, and you see them in textbook written in one dimension. But of course, for a polyatomic molecule having n atoms, there's really 3n minus 6 coordinates of this potential energy surface. So they're very large energy surfaces. So the first thing that we talk about is how to find minima on these surfaces, because the local minima are the geometries of the reactions and intermediates and products of chemical reactions. And these finding local minima, the general strategies are to sort of walk along these potential energy surfaces downhill in all directions until you find a point where the gradient, that is the derivative of the energy with respect to all of the internal coordinates, vanishes, and where all of the curvatures, it's called the Hessian, the eigenvalues of the Hessian matrix are the curvatures, where all these curvatures are positive. So we want to be able to find local minima, but also on potential energy surfaces, it's very important to find another kind of point called a transition state. And these are points, or geometries, at which all of the gradient components vanish again, so the derivatives with respect to all of the internal coordinates are equal to 0. But one of the Hessian eigenvalues, one of the degrees of freedom, one of the coordinates has a negative curvature, and all of the remaining 3n minus 7 degrees of freedom have positive curvature. So those are transition states. And then there's another kind of region of potential surface that's very important to be able to characterize, and these are called surface intersections. These are geometries that lie not within the 3n minus 6 degrees of freedom space, but at a lower dimensional surface where let's say two or more potential energy surfaces will intersect. It's usually two surfaces that intersect. And this has to do with maybe where a singlet and triplet surface cross one another, or where two singlet surfaces intersect in a subspace of dimension lower than 3n minus 6. And at these surface intersections and near them are where radiationless transitions or surface hoppings between one electronic surface and another are very likely to occur. Another thing that we need to be able to do on potential energy surfaces is when we find local minima in transition states, and we characterize the surface locally around these points as a parabola, that is a harmonic potential along the 3n minus 6 or 3n minus 7 degrees of freedom, then we want to be able to treat the local harmonic vibrational motion along these internal coordinates at an equilibrium geometry of a reactant or product or intermediate or even a transition state. So to do this, we have to solve the so-called Newton's equations of motion for harmonic motion. We talk about kinetic and potential energies along these individual 3n minus 6 or 3n minus 7 coordinates, and we carry out a harmonic oscillator vibrational analysis for the energies and the normal mode eigenvectors. The eigenvectors tell, for a particular vibrational motion, what amount of each of the 3n internal or Cartesian coordinates of the individual atoms are involved in that particular motion. We find that sometimes the symmetry in the molecule, the point group symmetry, can be used to break down or to decompose this problem of normal mode analysis into components that are like, for example, of A1 symmetry, B1, or B2. So you can use symmetry to subdivide the problem. So we have to learn about using point group symmetry there. And then we also talk about what are called reaction paths. And these are paths that couple or connect a transition state to a reactant or a product geometry. So the way to think of them is they're sort of like stream beds that connect a col or a pass in the mountains, that's the transition state, down to a base camp that is a reactant or product geometry. So characterizing reaction paths and how to map them out in a continuous manner is part of the discussion in this chapter too. And then finally, of course, there'll be a summary of the chapter, just like there always is.